Artificial intelligence has conquered games like chess and Go, but mathematical reasoning remains an unconquered frontier requiring advanced logic and creativity. That's why AlphaTensor, a new AI system from Google's DeepMind lab, marks a pivotal breakthrough. By combining innovative techniques, AlphaTensor achieved Olympic-level performance in challenging geometry problems and suggests machines are making strides towards flexible human-like math intelligence. DeepMind's approach to teaching AI math. Symbolic AI relies on human-authored, logical rules to methodically reason through multi-step problems. This mimics the deductive proofs used by mathematicians. Symbolism grants AI fundamental logic and causality to construct formal explanations step by step. However, these rigid rules struggle to handle novel or ambiguous scenarios. There is no flexibility to improvise or handle open-ended problems. In contrast, neural networks identify statistical patterns across huge datasets. Their flexible pattern recognition allows intuitive leaps in reasoning beyond formal logic. Yet neural networks lack mechanisms for verified logical proof or sound casual reasoning. Their simple efficiency also limits generalization capabilities. DeepMind hypothesized that combining symbolic system and neural networks into an integrated framework could prove revolutionary. The rigid formal logic of symbols provides sound deductive capacity, while neural networks add intuitive flexibility. Together, this hybrid approach possesses the full suite of skills vital for mathematical reasoning, rigor, logic, insight, and creativity. Concretely, AlphaTensor's technology stack utilizes: first, a state-of-the-art symbolic engine tailored for geometry theorem proving. This formally encodes rules like distance in triangles to enable logic-driven deductions. Second, large transformer-based neural networks handle fuzzy pattern recognition. If destructive proof fails, these creative suggestions help reformulate stuck proofs by identifying geometrical regularities. Third, orchestration algorithms combine symbolic and neural components into a cohesive system. This meta layer monitors proof progress to determine when to invoke each AI type's specialized skills. By synergistically blending reasoning approaches, AlphaTensor achieves far more than either could separately. DeepMind finally unlocked the tools necessary for an AI system to demonstrate human-level skill across the full spectrum of mathematical cognition. The culmination of a 5-year research effort to tackle this monumental challenge. Powered by hybrid AI, AlphaTensor's flexible yet rigorously logical reasoning pushes the boundaries of what machines can comprehend. Overcoming the data barrier. A persistent obstacle facing AI researchers is the lack of sizable training data in specialized domains like math. Modern machine learning techniques rely on exposing algorithms to millions of examples to learn effectively. Unfortunately, amassing such large math data sets is infeasible. Collecting hundreds of thousands of geometric proofs or Olympiad problems is well beyond practical human annotation efforts. Past attempts at mathematical AI floundered due to data scarcity. Without sufficient training examples, systems fail to learn the intricacies of representing and reasoning about complex formulae. DeepMind understood that limited data posed an absolute barrier to progress in this domain. Their ingenious solution was to procedurally generate synthetic training data rather than manually creating examples. Specifically, DeepMind programs scrapers to automatically construct geometric diagrams and proofs using formal rule sets. With this setup, they could mass-produce an essentially unlimited supply of novel practice content on demand. The scale of DeepMind's synthetic datasets strengthened AlphaTensor's robustness substantially. With such sizable training resources, the system generalized capabilities more stably than otherwise possible. This data abundance better etched core geometrical concepts into AlphaTensor's reasoning, a foundation supporting its strong empirical performance. Analyzing AlphaTensor's capabilities. Examining AlphaTensor's success in more detail reveals insightful takeaways. It developed problem-solving heuristics beyond formal rules, indicating flexible reasoning about when to follow conventions versus improvise. The system learned high-level strategies like reformulating problems and adding construction elements. These metacognition skills are hallmarks of mathematical creativity. AlphaTensor constantly created valid proofs, reaching correct solutions through formally valid logic, not just pattern recognition. This suggests real progress in teachable mathematical reasoning. Overall, AlphaTensor displays a cluster of distinct reasoning capabilities necessary for advanced mathematics: logical deductions, intuitions, insights, and creativity. Multifaceted mathematical reasoning. What's perhaps most impressive is how AlphaTensor blends different mathematical problem-solving approaches that were previously seen as incompatible for machines. Logical deductions through symbolic reasoning, flexible intuition, and pattern recognition via neural networks, creative insight to reformulate problems and implement new-age solution strategies. By combining strengths from different techniques, DeepMind creates an AI system with remarkably multifaceted reasoning. AlphaTensor signals that integrating hybrid AI architectures could produce more broadly intelligent systems. The wider implications for AI. Stepping back, DeepMind's work here has huge implications for the progress of artificial intelligence. It demonstrates that hybrid AI systems can unlock reasoning capabilities in difficult domains like mathematics, where prior approaches struggled in isolation. This cross-pollination of techniques is essential as AI tackles more complex challenges. Creative mathematical problem-solving remains an elite human ability. AlphaTensor's flexible human-like reasoning hints that more broadly intelligent systems aren't an impossible dream. Automatic data generation and simulation environments may be a recipe to expand narrow AI, as machines target reasoning abilities rather than just pattern recognition. Leveraging synthetic data could prove invaluable. If creative mathematical thinking is within reach, other high-level reasoning faculties assumed to be off-limits to AI may soon be achievable sooner than we imagined. Fields like science, engineering, and strategy may see disruption from AI sooner than anticipated. The road ahead. This work on mathematical reasoning is some of the most exciting AI research in recent years. We seem to be hitting an inflection point where combining existing techniques is unlocking more expansive machine intelligence capabilities. Looking forward, there is still an immense amount of work to translate this into directly useful applications. Pure mathematical reasoning alone doesn't result in helpful consumer products, but it could better inform designs, predict scenarios, and turbocharge R&D pipelines. The luminaries of the AI world are paying attention. Demis Hassabis, CEO of DeepMind, said AlphaTensor is one of the most technically impressive things we've ever done. Fifi Lee, co-director at Stanford's AI lab, highlighted that this is an historic result that will be remembered and celebrated. As AI rapidly becomes more capable at human-dominated skills, the cracks are starting to show in our ideas of guaranteed human superiority. If creative mathematics also fall, what reasoning frontiers still remain in our unique domain? It will be fascinating to see what barriers intelligent systems topple next. This breakthrough in mathematical AI signals a sea of change in what computers can comprehend. DeepMind has achieved a flexible reasoning system rivaling human skills, demolishing notions of guaranteed human superiority. While applications remain distant, combinations of AI techniques are unlocking new frontiers in machine intelligence. Remember to like and subscribe as we explore revolutionary AI achievements.